Hi, thank you everyone. I'm Hai Chao. Today I'm gonna present our CVPR 2026 paper, LinkedOut, linking what knowledge representation out of video LLM for next generation video recommendation. This is the work I did in internship at LinkedIn and collaborate with University of Wisconsin-Madison and Microsoft. Let me first briefly introduce myself. I'm a fifth-year PhD candidate in computer engineering at Northeastern University. Uh, my research topics including efficient video LLMs, word models, trajectory prediction, embodied AI, and more, and more. So today we mostly introduce LinkedOut. It's a paper that's integrating the video recommendation with video large language models. First, let me give some quick background about the recommendation. Um, the motivation of our work is because recommendation models increasingly lead to reason about visual content rather than only historical coherence. Current short form video candidates are dense, multimodal, and highly diverse. And for the recommendation system, cold start and non-tail item require semantically feature before interactions accumulate. And useful singular live may live in objects, actions, things, style, and context. And the serving path must still remain lightweight enough for online ranking uh, due to the quick reaction to current recommendation system. However, current pipelines treat the fidelity, knowledge, and scale. Why current pipeline for short? First thing is the label-centric features discard most pixel level cues. Second is text summaries create language bottleneck for visual details, and direct video large language model ranking too slow for multi-video histories. As you can see here, the current video recommendation architecture usually use a simple video classifier to predict the classification results as tag and feeding that into a recommendation model for faster inference and recognize the necessary tag from the video input. Where another kind of current video recommendation, they use a pre-trained video encoder to extract some video features for the recommendation model. Some work start to um, integrating the video LM for recommendations, but there is not a lot of works. Those work are usually either treating video LM as captioning to summarize to generate text summarization from video input and pass the text into recommendation, or they just simply uh, feed all the multi videos input into visual large language model and directly ranking results. The C and D is just some potential video LLM architecture for recommendation. However, those work either cannot capture the details about the video, or they are too heavy for the video LLM to process. The missing capability is a compact server-friendly representation that still carry video LLM's word knowledge, while they don't need to rely on the video classifier or video encoder for limited knowledge inside a small dataset. This motivates linkout, which we're trying to extract the video large language model's knowledge from raw pixels without turning the entire problem into text generation or online VLM inference. So here is two implement way for current for our idea. And the insight here is intermediate VLM hidden state contain visual and semantic pairs that can be exported as compact video features. Uh, so we uh, we just take the video LM video input and feed it into video large language models and fuse it and get a very compact link out feature and feed it to recommendation. This can avoid a text-only bottleneck by extracting representation directly from VLM layers, and this can use multiple layers because semantic depth varies across the network. And for the serving-friendly architecture, this architecture can allow us to pre-compute and store compact embeddings so the online ranking stays lightweight. We can just store the link out feature for each video in a code base, and during the serving, it will be very fast for inference and retrieval. And the and and for the multi-layer part, we can just see the E part, the VOM for token extraction. Like if we use last tokens or token from last layers or token from multi-layers, if we directly use that without a compact representation, the recommendation system cannot take that much tokens, and the reference might be very slow, and it cannot use multiple layers because the needed semantic may not exist in the last layer, but exists in the intermediate layer. So the VLM looks just like a feature factory, not a serving time recommender. That's why we need to do our work. So here is the methodology overview. Basically, we follow a pipeline that extract, compress, fuse, and store and retrieval. Raw frames and optional prompts pass through a frozen VLM, and LinkedOut exports compact video embeddings. The pipeline is the video is we extract the old and generated video LLM tokens and compress each selected layer to fuse semantic depth with MOE, and then store embeddings for online ranking. Here is some more detailed overview about our proposed architecture. The first model is word knowledge aware video representation. It starts from raw frames and optional prompts, and then extract VLM layer tokens. The model takes the raw video frame rather than the only labels or captions, and it allows optional text prompts and descriptors when available. And it runs through a frozen VLM backbone to expose rich hidden representations and produce old token feature and generate token feature for selected layers. So basically, the raw video frames feeds through this part, and the text prompt input can taken prompt-driven queries, and other multimodal information can be expressed by the text prompts, and it can also include some metadata like additional model descriptors or just some dynamic text that changing, evolving the time. So the design of this architecture is the design goal of this architecture is to preserve pixel level visual details while linking it to VLM word knowledge. And some detail about the model one intermediate layers expose different semantic depths. Unlike most VLM, just use the final layer representation or use the text summaries or text response from the VLM. The link out representation is not restricted to the final generated token. It actually uses multi-layer token from the LLM part of the whole video LLM. Why we use multiple layers? The first reason is the final output can be overly compressed or just language based. Many information that exist in the lower and the middle layer retain richer visual structure and compositional cues, but during the language forming part, those rich information are just dropped to generate a text response. And the generated token and old token carries complementary recommendation evidence, which might be helpful for us to use during the video recommendation process and other downstream tasks. And the layer choice, if we don't use the last layer, the layer choice might be through experiment or manually select, which is not ideal. So we just use this, uh, uh, make it become a learnable modeling decision rather than just a fixed heuristic. So as you can see in the architecture, the intermediate feature from the LLM part for the video LLM just extracted and sending into for each layer and sending it to a layer talk compressor expert and passing it to a cross-layer knowledge MLA future and get a final very compact word knowledge feature and send it to a vector database to implement the store and retrieval pipeline for faster serving. And the semantic depth matters because the best layer for language generation is not automatically the best layer for recommendation, as indicated in many other papers. Um, the second model we propose is a layer K token compression expert. It's extract the per layer. It's a per layer expert merge old and generate token into a compact representation to compress it through in compress it inside the layer to make sure the model can extract make sure the model can extract the compact feature in that layer. So it's processing token features from each selected layer and merge existing token features and generate token features. And it uses selected expert to retain text relevant information and control representation size before cross-layer fusion. The compressor is a bridge between high-dimensional VLM internals and the recommendation-friendly features. The layer K is just one layer inside the VLM, which typically 24 layers inside the 7B VLM. And the orange part is the features from what we call old token. Is actually is in the encoding process of the transformer layer, and the generated token features is actually generated through the autoregressive token. We believe that orange token might be doing the in extracting thing, and the uh, blue token may generate more query specific information because they are generated through AR process through all the tokens. So the token goes through a token merging model and then pass it to a projection layer. And then the selection airport from both old and new token and generated token just compute a very compact token to represent these layers information. And the transformer is fully trainable, so it can dynamically select the necessary information for the task for this layer. And the Model 3 is cross-layer knowledge fuser MOE, which gated fusion selects useful semantic depth across VLM layers. The role of this fusion model is receive compact representation from several layers and learn layer level soft gating instead of hand-picking one layer. And it output one link-out feature with word knowledge and gate with provider routine to interoperability. For every layer, it will assign a layer encoder, uh, and the layer soft gating will compute the weights for each layer and generate a final link out feature by selecting the necessary knowledge inside each layer. So this model converts many semantic depths into a single ranking and a single ranking ready video representations. So the end-to-end merging from VLM feature to online ranking is uh, this is show extraction, compression, fusion, storage, and downstream recommendation. And dur- during offline, the VLM feature extraction plus model computation, and during online, its retrieval, the compact feature from a vector database and run the recommendation model. So to by doing that, by doing the store and the retrieval architecture, this model turns a large multimodal model into a reusable video feature source. So here is the detailed serving design for the store and the retrieval. Uh, it's implemented by pre-compute compact VLM drive the feature offline and it keeps the online. In that way, it can keep the online ranker lightweight. This is important because direct VLM ranking does not scale to multi-video histories or large candidate sets, and compact video feature can be refreshed offline and retrieved online. And the online ranking sees dense representation, not raw features or generate summary. And this makes VLM knowledge compatible with millisecond scale serving. So during the online in the online part, the model just goes through the whole video database, like the one used in LinkedIn video or used in TikTok, and generates the word knowledge feature for each video, and it store it inside the vector database in a like daily routine, because the video the video number is fixed and gradually added. And by doing so, we can isolate the video LM from the model needs online serving. That the model that leads to react very fast do not need to call the VLM, but just look into the vector database and take the user features and quickly give the relevant score. So, and our ex by our experiments and our serving climb to validate letter shows linkout reports 5.94 964 ms online latency through through the store and retrieval architecture design. So here's some results about our work on the microlens benchmark. Compared to ID only and video recommendation baselines, our model achieved the better performance, the SOTA performance across all kind of across four kind of video recommendation reported in the microlens benchmark. The roles over ID based and video based recommendation uh, is the type of ID based and video based recommendation baselines, and the metric is HR10 HR and NDCG is some is a metric related to the hitting rate of user behavior. If a user hits the video uh, in top 10 results, is this in top 10 results, then HR at 10 will count as true. And if it's in 20 video generated by the recommendation models, it will appear in the HR at 20. So the linkout rows is consistently strongest in this table, and the highline lift report uh, is larger than the other baselines compared to the baselines. So this shows the linkout turns VLM methodology into measurable ranking improvement. So we also compare it across the different data sets because there is a lot of currently most of video recommendation data sets they don't support raw video. So we compare we search public data set and only find the microlength 50K and microlength 100K. So this table is focused on the compression of model type and dataset size, and the LinkedOut remains strongest on both 50K and 100K settings. And this pattern supports the claim that VLM derived features are not only data-specific to the artifacts, but consistently show outperform across the baselines appear in the both dataset. So we do some ablation study to show if each component is in our architecture is necessary. So the first variant is we only use the last layer and the last token as to feeding into the feeding into the recommendation model as baseline, or we just skip our token compression, or we replace our token compression models and just use the mean polling plus MOE to test the model. And or we just pass the last token, not select the necessary token uh, inside each layer of VLM and pass it to MOE. And it shows with this model drop, with this architecture drop, the performance drop greatly. That indicates the compressor and the cross-layer fusion do matters in our architecture. And we also do some analysis to show the importance of each layer, the multi-layer, uh, uh, the the multi-layer design of our architecture. So we visualize this by analysis of MOE gates to reveal where the useful recommendation evidence constraints. So the so by by showing the normalized layer contributions by looking into the MOE gates weights, we can see the the LA takes most important part, which is the middle layer. It takes more than 40.9% of attention after normalize contribution to the final knockout feature after normalized. And each layer contribute different corresponding to different tasks, but to the recommendation task is and on this dataset it shows each layer contributed to the final results. And the layer 8 contributes more than 30% in the analysis, highlighting the value of intermediate the VLM semantics. And the multi-layer middle layer capture visual semantic structure that the final output compressed away, and the layer contribution gives a diagonal view of the representation. This supports the design choice of learned cross-layer fusion. And here is the analysis of probability density for MOE gateways. This gate distribution shows a layer selection behavior rather than a uniform average rule. The layer specific density shapes indicates non-uniform gate behavior, and the filter is not simply average all layers equally. The distribution view complements the contribution box plotting from last figure, and this makes the representation more intractable than the black box polling embedding. So the MOE it indicates the MOE gating provides both performance and a way to inspect the semantic depth usage. And here is another ablation study to show the speed up of the store and retrieval architecture. If we use directly VLM-based model, which we just directly test with VLM directly, because there is very few work there. So it needs 5.5 seconds for one video because VLM inferences the air process and the multimodal token is very huge, so it's very slow. And for traditional video recommendation, since they are only a very small model, it's only needs 0.8 ms for each video. Uh, and after our store and retrieval architecture, by integrating the VLM, it's only need 5.9 ms for each video, which is 1,000 times acceleration compared to directly use VLM base. So this may not be the many people say the store and retrieval architecture may not be have novelty, but if we use it in real world scenarios, it has truly speed up for the current serving architectures. And here is future insight and the following works. Actually, I think the VLM plus a small model is very useful, as proved by this work and other work and our other following work like ThinkJPA. And this architecture shows that using multi-layer intermediate feature and using the VLM and guidance for the small model is getting more and more attention these days. So I hope this can help you provide you some insight and for your work. Yeah, and that is all the presentation today. Do you have any questions?